Hi and welcome to one of ARM's AI Tech Talks, bringing you the latest in AI trends, technologies and best practices from ARM and our ecosystem. Make sure you subscribe and hit that notification bell so you don't miss any of our upcoming talks. And don't forget to view the playlist too in the link above. I hope you enjoy this Tech Talk.
Hello, good morning, everybody, or good afternoon, wherever you happen to be coming in from today. We're so glad that you're here. Welcome to those who have never been here with us before. If this is your first Tech Talk, welcome. And for those of you who are returning, it's great that you're here again. So today we've got a fantastic presentation from our ARM research team. We only get them like twice a year. And so whenever they are here to talk about some of the stuff they've been working on, it's really interesting. This is, it's always very cutting edge, and I'm always learning something new from the research team. So I'm really excited to have them here today. And today we'll be learning about unified DNAS for compressible TinyML models. And this is really exciting. This is leveraging ARM's new IP technology that comes with our U55. And today we have Igor Fedorov, who will be presenting today. But before we get started, I just want to show you, give you our Twitter handle and our YouTube channel. So if you want to tweet it and give us a shout out, please do while you're watching this or after. We might give you a shout out back. And this is also the link where you can sign up for our upcoming virtual Tech Talks. And I'll give you a preview of those. So next week, we've got Kikso, who is going to be talking about how they've integrated with our ARM virtual hardware, which is going to be really, really interesting for developers who are interested in using ARM virtual hardware. So don't miss that. Keeping on the Ethos U55 theme, we've got object detection coming from EMSA. And then Plumerai, DeepLight, and Lodestar are going to come, and we're going to have a bit of a different presentation. It's going to be a panel session with these leaders, these startups that are doing computer vision on the edge. And it'll be a really interesting discussion. They'll be talking about, challenges, where they see the industry going, and some of the new stuff they're working on. And then in June, end of June, we've got Noda, which has a great ML product, Nespresso, and they have a really interesting way to design neural models, and they are going to come and tell you all about it. So sign up for these, put them on your calendar, and come join us again at any of these sessions. So with that, this is Igor Fedorov. Hey, Igor, how you doing today?
Hello.
Igor's our staff research engineer in our research lab, and he works on neural architecture search algorithms, and he holds a PhD in electrical engineering from University of California in San Diego. We were just chatting before this about the topic he's going to be discussing today, and you're in for like some really good information here. You're going to learn a lot. So please ask questions. You can use the Q&A box to put questions in. We'll take questions at the end, but we'll also take questions during the presentation. So if Igor mentions something that you have a question about, pop the question in, and we'll get that question asked throughout the presentation. And so let's get started. I think that's all from me. So Igor, I'm going to hand it over to you, and go ahead.
Okay. Thank you for the introduction. I'm really happy to be here. So the subject of this talk is going to be neural architecture search. And so before I begin to sort of dive deep into the technical details, I first want to start with some motivation. So why does neural architecture search matter? Well, the first big reason is that deployment onto resource-constrained hardware requires specialized models. Basically, when we're talking about embedded hardware, we have very limited memory, limited computational power, but traditional neural networks, they can have lots of parameters, lots of operations, and so they simply don't fit onto the hardware. They run too slow, and so we have to design special models that can be deployed to this kind of hardware. The second reason why neural architecture search matters is because it's much easier to iterate on better models compared to iterating on better hardware, which can be quite costly and requires a lot of time. And then third, at least from our point of view, neural architecture search can be an important tool to evaluate potential hardware features. So, for example, we can ask questions like, if the hardware supports models with some new features X, what improvement in task performance can be expected? And if this improvement is very high, then the engineering effort that would go into designing this hardware feature is justified. Okay, so what exactly do I mean by the neural architecture search problem? So we begin with a set of hardware constraints. So these are constraints on the model that come from the fact that we're trying to deploy onto a specific hardware platform. And so examples of hardware constraints include things like limited model size. And this comes from the fact that the hardware has limited flash storage memory, which limits the number of bits basically that we can use to store the model. The hardware also has limited RAM memory, which limits the size of the activations produced by the model. Also, when we're deploying to hardware, we care about things like latency and energy, which are also impacted by the hardware capabilities. Okay, so given these hardware constraints, we basically care about designing accurate neural network architectures that do well on some target task that we care about and that fit into the constraints that we specified. Now, the additional interesting thing that we should consider is the fact that we can apply model conditioning algorithms to any neural network architecture to make it more hardware friendly. So for example, we can apply techniques like structured or unstructured pruning to make the model smaller, faster, more energy efficient. We can quantize the model's weights also to make the model smaller and to, for example, use integer math operations instead of floating point math operations. We can cluster the model's weights to reduce the storage size of the model. And each one of these model conditioning techniques comes with its own training algorithm. For example, if we want to quantize the model to 4 bits, we need a special algorithm to train that 4-bit model. And so basically these three things, the hardware constraints, the fact that we want to design architectures that fit these constraints and that we're allowed to employ model conditioning techniques for each architecture, they set up a sort of search space. The search space is quite vast and requires a search algorithm to traverse the search space. And it's important for this search algorithm to be scalable. And when I say scalable, I mean it in 2 ways. So first, as the size of the data set grows, so the size of the actual task that we care about solving grows, we want the search cost to basically not explode. So we don't want the search cost to grow like exponentially with the size of the data set, because otherwise we wouldn't be able to solve large problems effectively. And the other way in which the search algorithm should be scalable is in the size of the search space. So as we expand the search space, the algorithm should scale nicely with that growing search space. It's also important for the search algorithm to have some features like trading off exploration with exploitation. So search algorithms have this property where they need to explore the search space, which is vast, but they also need to hone in on some small portion of the search space. And basically, given that we have finite computational power and finite time, we have to do this sort of trade-off where we begin by exploring the space as much as possible, and then slowly moving to exploitation mode where we narrow in onto some small portion of the search space. And lastly, the search algorithm should be robust to hyperparameter choices. And this is because the actual search process is very computationally and time intensive. So this can take like weeks or months to run. And so we simply can't afford to spend lots of time to tune hyperparameters for the search algorithm itself. And then lastly, all 4 of these pieces need to be implemented in an efficient unified software framework that's able to sort of conduct the search in a very efficient way. And for the purposes of this talk, I'm just going to focus on one of the hardware constraints, which is a constraint on the model size that comes from the limited flash memory in the hardware. And I'm going to focus on this constraint for two reasons. One is because I'm going to exploit this new feature in ARM NPUs, which allows for model compression. And the second reason is also because basically it will make the explanation sort of easier, but it's all of the arguments and all of the algorithms that I'm going to present, they can be extended to cover all sorts of hardware constraints, and not limited to just this one constraint that I'm going to talk about. Okay, so what do I mean when I say a compressible model? So let's say we have a neural network. We can take the weights that parameterize this neural network, and we can apply weight compression to those weights. So basically, we can apply a data compression algorithm to reduce the number of bits needed to store that neural network. And then we could store it in memory. And then during inference, the hardware can decompress the weights of that model and reproduce the original model that we started with. And the important thing is that this decompression is done efficiently and very quickly. So the newest NPUs, the Ethos NPU, have this feature where they're able to decompress weights from memory. So given that we're able to apply weight compression to a model, the question becomes, how do we minimize the storage cost of a model? So we have several different strategies that we can employ here. For example, we can just begin with a very small architecture. So we can think about architectures that have a very small number of channels, or have a very shallow, don't have a lot of layers, or that use parameter efficient operators, for example, like depth-wise separable convolutions instead of regular convolutions. On the other hand, we could take a large architecture, but have the weights that parameterize that architecture have very low entropy, meaning that the weights are very compressible. And some ways to do this could be by setting a lot of the weights in the architecture to 0, or making the weights sparse. We can also quantize the weights in the model to very low bitwidths, which will also reduce its storage cost. Or we can do a combination of the two. And the third thing, the third strategy that we have is basically to do something in between. We can have a medium-sized architecture where, let's say, some of the layers have very high sparsity and have low entropy, so they're more compressible. So basically, the search problem is to select which of these modes we should be in for each of the layers in the model. So stepping back, what's the actual goal at like a sort of a system level that we're trying to achieve? So we start with a hardware platform that has a processor and memory, and the other thing that we care about is basically the data set. So in this case, let's say we care about classifying images from the ImageNet image classification data set. So given the hardware and a task, we feed the hardware requirements and the data set to our algorithm, which we call UDC, and it produces a neural network. And this neural network is compressed and then deployed to the actual hardware that we started with. And in this case, the compression is done by a special compiler called Vela, which is specialized specifically for the Ethos NPU. Okay, so why use our approach versus others? Basically, the big reason is that it works very well. So here I'm presenting the results. So basically, these are models that our algorithm has designed automatically. And I'm comparing our results to a bunch of other results in the literature in a model size versus accuracy Pareto. So our models are in blue, and you can see that our models are more accurate and smaller than all of the existing approaches out there, where the existing approaches include a mix of different methods that do anything from neural architecture search to quantization to weight compression, or a mixture of all those things. And the other reason why we should use UDC is because it has a lot of really nice features. So we can compare UDC to the state of the art in model conditioning and model design literature. And we see that UDC has lots of properties, like it's able to search over the width, operators, and depth of the model. It can search over the bitwidth and sparsity rate for each layer in the model. It's also guaranteed to meet hardware constraints. So other methods in the space do sort of like a regularization approach where you can run the search and get a model, but it can be, let's say, too large, larger than you expected. And so you have to rerun the search many times to get a model that's actually small enough for your hardware. And that search process ends up being very costly. The other really nice thing about our approach is that it discovers models that are employable with integer math only, as opposed to other approaches which do things like non-uniform quantization that can't be deployed with integer math on commercial hardware. And then lastly, we target very, very small models, like less than 1.5 megabytes. Okay, so how do we actually accomplish this goal? So we begin by setting up a search space. And so at a high level, the search space can be thought of as like a combination of layer level search spaces. So for a given layer in the model, we consider three different things. We consider the bitwidth that we should quantize the layer's parameters to. So in this case, I'm showing a search space example where we consider quantizing the weights for the layer to 1, 4, or 8 bits. And then secondly, we also consider the sparsity rate for the layer. So how many zeros should we have? What percentage of the weights in the layer should be 0? So here I'm showing an example where I'm choosing between 98% zeros, 90% zeros, and 50% zeros. So these two decisions get combined and fed into an operator. Here I'm showing a convolution operator, and then usually that goes through a batch norm, and then that leads into the third decision to be made at the layer level, which is the number of actual channels to use. So here I'm showing an example where we're choosing between 8, 16, and 32 channels for a given layer. And the interesting thing is that this represents what's called a weight sharing mechanism. So basically, we have just one weight tensor that parameterizes this entire layer, but we have 3 different decisions that depend on this weight tensor. Notice that this weight tensor isn't replicated 3 times for each decision. And so this is very efficient because basically we don't have to grow the number of parameters in the model to do this search. And that goes back to the scalable search approach, which I said was very favorable. So basically what we do is then we stack this layer level search into a large network, what's called a supernet. And this represents a second form of weight sharing because the decisions made at layer 1 impact the decisions made at layer 2, but you don't have to replicate the search space in a combinatorial kind of way. So we can make the decisions jointly in layer 1 and layer 2 together, and that's another form of weight sharing that makes this algorithm scalable. Okay, so I don't think we have too much time to actually delve into more about how we do the search, but one interesting thing that I wanted to touch on is once we actually do the search and we find models that are compressible, that are let's say sparse and have a very low bitwidth, how do we actually train these models? So in order to kind of get some intuition about why these models are hard to train, let's suppose that we have a neural network that we train, and we take one of the layers in this neural network and we quantize it, and then we prune it to, let's say, 90% zeros. So what would that look like? So here I'm showing a histogram of the weights in this layer. That histogram is in black here. And then in red, I'm showing the quantization bins. So this is what would happen if we quantized the layer to, let's say, 4 bits, which would be 15 unique values. And then in purple, I'm showing the boundary between which everything gets mapped to 0 because we're pruning 90% of the weights to 0. And so here you can sort of get a sense of why it's difficult to train models like this. So we see that most of the model's weights are going to be 0. And then for the non-zero weights, we're only using 2 of the quantization bins, even though we have well, we were using 4 quantization bins if you consider the positive and negative orthant, but we have 15 that we're allowed to use. So we're basically wasting a bunch of the quantization bins because we're actually doing this pruning. So this is sort of what happens when you take a pre-trained model and you prune and quantize it. So what would happen if we now let this model be trained by something like stochastic gradient descent, where the optimizer gets exposed to the noise from this pruning and quantization process? So what happens is that the distribution of the weights sort of gets flattened. You can see these weights look sort of Gaussian, and then once we train with pruning and quantization in the loop, we get this sort of flat distribution. And you see that the weights get pushed out sort of, and more of the quantization bins end up getting used. So now we're using 3 bins in the positive orthant versus just 2. So this comes at a cost because the range of the weights has increased dramatically. So you see before we let the optimizer train this model, we had a range of about 0.1. And now the range is like 0.25 or 0.3. And we can actually quantify the increase in the magnitude of the weights by looking at the L2 norm of the weights. And we can see that the L2 norm of the weights increases more than 4-fold from the pre-trained model to the model that's trained with quantization and pruning. And the reason that this is not a good thing is because models whose weights are very large learn very slowly, and they're not able to recover from the noise that's added to this model from the quantization and pruning processes. So our proposed solution is to change the way that we do the quantization and spend the quantization bins only in the region of the signal that we care about. And what that basically looks like is shown in this subplot. So here I'm showing that we're still doing the pruning, and everything between the purple bars gets mapped to 0. But the uniform quantization now happens only in the unpruned weights. And it's done uniformly still in both the positive and negative orthant. And the interesting thing is that if we train the model with this kind of quantization, then the norm of the weights doesn't increase as much. So you see here that it's about half of the norm of the sort of the baseline approach. And so this means that networks that are quantized this way can actually be trained faster. And while I don't have time to get into this here, the other interesting thing about this approach is that it can still be deployed with integer math only, even though if you just look at this, it's really not a uniformly quantized signal. But as we outline in our paper, which is you can find on arXiv, there are several strategies which can be used to deploy this models that are quantized this way with integer math only. And we can actually look at the impact of just this quantization strategy alone on the accuracy of models. So here I'm showing 2 models, which for a given model size are identical, but just trained with either the uniform quantization, that's like the baseline approach compared to our proposed quantization. And we see that the accuracy on the ImageNet dataset goes up significantly using our proposed approach. So as much as like 6% for this 0.5 megabyte model. Okay, so let's jump to some more results for our approach. So as I showed before, we can do ImageNet classification quite well, and we can find models that are Pareto dominant in a model size versus accuracy sense. But the other kind of interesting thing that we can look at is what are the decisions made by the algorithm at each of the layers in the model. So we can look at things like how many channels are used at each layer, how many bits are used to quantize each layer, and what's the sparsity rate at each layer. And so that's what's being shown in these subplots here. So in the leftmost one, we have the percent of the non-zero channels at each layer. Here we have the bits at each layer, so choosing between 4 and 8 bits. And then the rightmost one, we have percent non-zero weights. And pretty much what you see is the general trend is to use more channels, more bits, more non-zeros at the beginning of the model. And then towards the end of the model to use less channels, less bits, and less non-zero weights. So we can also run our algorithm to find SciFar 100 models, which is another image classification task. And here again, we find models that are Pareto dominant with respect to state-of-the-art model design algorithms. And the last use case that I wanted to show is actually not a image classification use case, but a super resolution use case. So this use case is where we're given images that are low resolution and we basically upsample them to be at a higher resolution. And here, instead of comparing the models based on their size, we compare them based on the number of multiply and accumulate operations that are used during inference. And the reason we use the multiply and accumulate measure here is because these models are already quite small, and they're actually we care less about minimizing their size and more about minimizing their latency or the number of multiply accumulate operations. And what we see here is that our approach produces again models that are more accurate and smaller than existing models. Here the vertical axis is the peak signal to noise ratio. So basically our approach is doing a better job of producing these high resolution images. And then the last thing to note here is that since at the beginning I mentioned that our approach is not tailored just to one kind of hardware constraint, this is showing that we can optimize both for model size and or something like multiply accumulate operations. Okay. Okay, so next I want to jump into some more results, and these are more like ablation results, which sort of highlight the different properties of the algorithm and give a better sense of how it's working. And the first thing to consider is basically to compare the search algorithm to a simple baseline like random search. So often we see papers in literature that are very complex search algorithms, but their search space is set up so that the search space includes lots of very good models, like it's very dense with good models. And as a result, a simple approach like just randomly sampling models from the search space could lead to very good results. And so what I did was I generated 100 models at random from our search space, and I compared them to the model that's discovered by our algorithm. And this is showing you a scatter plot of the accuracy versus model size on the SciFar 100 dataset. And what we see here is that our approach produces a model that's 5.5% better than any of the randomly sampled networks, which is good. But the other interesting thing is that this is showing that our search space is actually very diverse. So there's lots of models in the search space which aren't trainable at all. There's some models that are like very low accuracy, some models that are medium, and some that are high. So there's a very wide range of models in the search space, which means that the search problem is actually quite difficult. So it's another sort of good thing for our algorithm to be able to traverse a search space. But how fast does our algorithm discover these good models. So what I'm showing here is basically the accuracy of discovered models by the two methods as a function of the number of trials or the number of models evaluated. What we see here is that for the random search, obviously, as we sample more models, the best found model is more and more accurate. But interestingly, our approach is quite efficient. So it discovers the winning model, so to speak, in about 3 trials. That the number 3 basically comes from the fact that the cost of doing a search is about twice the cost of evaluating a single model from the search space. So we take those 2 trials plus the 1 for actually training the model. So that gives the 3. So what this is showing is that not only is our approach better asymptotically, but it's also much more efficient, even if we measure on something like how fast it takes us to actually find good models. Okay, so I think that there's a question.
Yeah, we've got 4 questions in one. So so Igor, do you want to take those now, or do you want to wait?
Yeah, let's see. I can take a few now. I guess we're about 35 minutes in.
Okay, so thanks for starting to post questions. This is exactly your chance to get all the details you need to know about this. So let's see. The first question is, do you use QAT or PTQ when doing the compression aware training?
So QAT is quantization aware training. I'm not sure what the acronym PTQ stands for, but we do quantization aware training for training the models. Yeah.
Okay. Is the DNAS able to handle discontinuities in the optimization function plans? And is it able to handle categorical and conditional variables?
Yes, definitely. So the entire search space is discontinuous, right? So it's all categorical because all of the decisions we have to make are like choices amongst a set of possibilities. So if you think about, let's say, quantization choices, we're choosing between, let's say, 4 and 8 bits for each layer. So that's a categorical choice. And conditional variables, yes. So definitely we support search spaces which have conditional relationships. So you can think of, for example, if we're searching for models with like if we're searching for the depth of the model and also the number of bits to use at each layer, then the choice for the number of bits is conditioned on the depth of the model. And so we definitely support that.
Great. And then next, going right in, what search function does UDC use, assuming it's not doing joint optimization of architectural encodings and weights?
Yeah, so the objective function that we use is optimizing over the architectural parameters and the weights. And the form of the objective has 2 terms. So one term is optimizing for the task that we care about. So let's say we care about image classification. So we would be optimizing for, let's say, the cross entropy. And then the second term is a very special regularizer. So it has a special form that basically guarantees that we meet the hardware constraint that we set at the beginning.
Great. And then lastly, how do you get the hardware constraints? Are you using real hardware, virtual hardware, Renaud or AVH, proxies or predictive models?
Yeah, great question. So I guess it depends on which hardware constraints that we're optimizing for. So let's say, for example, if we just want to deploy a model and we don't care how slow it is, so we would say we would constrain the model size and, let's say, the RAM usage of the model. So that would make sure that the model fits in memory, and then when we wouldn't run out of memory as we're executing the model. So that would come from like the device specifications. But if we care about something like the latency of the model on a specific hardware, then typically what we do is we build a predictive model of the latency as a function of the architecture on that specific hardware platform.
Great.
And, yeah.
Thanks for sending those questions in. We have a few more coming in. Do you want to take those now, or do you want to finish with your presentation?
Yeah, we could take them now. I only have a couple more slides, so we can.
Perfect. Cool.
Yeah.
I like the Q&A part a lot, so I'm glad we're continuing with that. So is your NAS able to also optimize feature projection blocks that are common in sensor processing, like parameters of DSP blocks?
Okay, that's an interesting question. So first, I just want to say I'm not an expert on DSP blocks, so I'm not exactly sure what feature projection blocks are, but assuming it's something like, let's say, choosing the dimensionality of the input features, like let's say choosing the number of FFT bins or something, then yeah, we could definitely frame that as a search problem over, let's say, number of channels in a layer or number of neurons in a fully connected layer. So we can definitely handle that sort of problem setup.
Cool. Okay, last question from Nick. What are alternative methods to the compound loss function you described to jointly optimize against statistical solution quality and architectural performance?
Yeah, that's a great question. So, so this falls under the category of multi-objective optimization algorithms, and there are lots of different alternatives. So there are different ways of doing scalarization, which is like where we combine multiple objectives into one, which is kind of what I described we do. So we sum them up. You can also take a product, and then you can also do things like something like random scalarizations, where you can do a sum, but the weights of the two terms in the sum are chosen randomly, and that can make your model sort of explore the Pareto frontier more. But basically, there's a whole literature on this, and we sort of chose one that's fairly popular and pretty robust, and experimentally works quite well in our experience.
Great. And Wei just jumped in with a question about training. Do you train from scratch, or can you do NAS with transfer learning? We don't have a big data set.
Okay. Yeah, certainly you can do like a transfer learning kind of setup. So you can do a search on a proxy data set, let's say. So if you don't have a lot of data for a particular, let's say, image task, you could take ImageNet, do your search there, get the architecture from the search, and then train it on your target task. That's definitely doable.
Awesome.
Yeah.
Try it out, Wei. Let us know if it works. Another question that just came in hot off the press is, there are lots of search strategies that are out there: reinforcement learning, DNAS, evolutionary, MCUNet, for example, and Bayesian. Which is suited to what hardware software application conditions? That's a big question.
Yeah, that's like a very fundamental question that I'm not sure is really I'm not sure you can really say that like any one of those approaches is in general better than another.
It seems conditional.
It
seems specific to the use case, I would expect.
Yeah, and like the opinions change with time. So I think Bayesian optimization. So I think evolutionary search and Bayesian optimization were quite big, and then DNAS came along and it became popular, and now Bayesian optimization is like coming back. So these things also change with time. The one thing I would say is that the performance of things like the performance of any algorithm depends on the search space and how, like I said, how dense the space is with good models. And what I've noticed is that a lot of approaches that do things like evolutionary search or Bayesian optimization, they use a search space which is very dense with good solutions. So it's whereas our search space is very sparse with good solutions. So I think that's an important criteria to measure algorithms. But I don't really have an answer to which one is better for a specific hardware software application.
Sure. And then Nick's back. Hey, Nick. He says, you mentioned surrogate models for architectural characteristics like latency. What degree of generalization can you achieve here? On one end of the spectrum, you can imagine generalizing between M3 and M4, but what about very qualitatively different architectures?
Yeah, so in terms of modeling latency as a function of architecture, the typical approach is to have a single latency model for a single hardware. So if we wanted to characterize the M3 and the M4, we would have separate models for each one. I think trying to predict the latency, so the latency of a given architecture on many different hardwares with a single model is like really, really hard. So yeah, that's the general approach is not to do that. It's just to have separate models for each hardware platform. Okay,
great.
I think that's it. Yeah.
Thanks, everybody. Yeah. Keep them coming. We still have some time for more questions. So Igor, why don't you continue and see who else asks something? Yeah,
these are great. Yeah, thanks. Okay. Right. So okay, so jumping back into this. So yeah, so this was showing that our approach is basically an efficient search algorithm. And the last ablation is basically about this compressibility issue. So when we're doing the optimization during the search, we have to make sort of an approximation to measure the compressibility of a model. And the approximation we make is with respect to how many bits are needed to actually store the model. And this approximation has to be differentiable with respect to the model parameters. So we couldn't just use like a compression algorithm directly in the loop. And the approximation we make is we say that the number of bits needed to store a single layer in a model is given by the number of bits that we quantize that layer to, plus the entropy of the unstructured pruning mask M times the number of elements in the layer. So this is how we measure models during the search. And so the first question is this measure actually realizable in the real world? Meaning, can this entropy limit be achieved by a real compression algorithm? And then the second question would be, how does this approach actually compare with the compression algorithm that's actually used to deploy models onto the NPU? And so for each of the models that I presented, I have a table here showing how the model size that we calculate. So for example, model 1, we calculate using this equation that the model is about 0.5 megabytes. So now if we replace this entropy term with a real compression algorithm, like an arithmetic compression algorithm for the mask, what's the model size we get? And again, we get the same model size, 0.5 megabytes. And if we actually use the NPU compiler Vela, which does the weight compression for deployment to the Ethos NPU, we actually get a smaller model. So here it's like 0.44 megabytes. So that's really good. So the model, we can actually achieve the compression that we were after on a real in a real deployment scenario. And the reason that this number is smaller than the model than the number I started with in our approach is because we were assuming that the non-zero weights basically are stored using B bits per weight. So meaning if we quantize a layer to, let's say, 4 bits, that we use 4 bits to store the non-zeros. But that doesn't account for any kind of like further compression that you could do of the non-zeros, which something like Vela can actually take advantage of. And that's why these models are actually, the models that Vela produces are actually smaller than the models than the models that we predict that we sort of like predict the compression algorithm would be able to achieve. Okay, so that brings me to the conclusion. So UDC is an automated, efficient method of designing neural networks for deployment onto resource-constrained hardware. and just some possible future directions that we're considering. So obviously, there's always more use cases that we can support, more data sets, more types of tasks that we can apply this algorithm to, as well as making the algorithm more push button. So meaning like have the algorithm even more robust to hyperparameter choices, require even less expertise to use, so in order to make the algorithm more widely accessible. And that brings me to the end of my talk. Thank you.
Thank you so much, Igor. We've had a couple other questions come in, so let's get to those. So the first one is more kind of a statement with a question. So it's been observed in some papers that NAS does not yield generalizable models. Further, NAS optimized models fail on different input spaces over hand-tuned models when aggregate measures such as accuracy is used to quantify model performance. Are there any techniques or better metrics that can handle these two problems?
Okay, so there's a lot in this question. So
there's a lot going on here. Yes.
All right, so I guess let me address this in pieces. So
yeah.
So the first sentence, it's been observed in some papers that NAS does not yield generalizable models. Okay, I guess I could see a situation where you could like overfit to a data set by tuning both the architecture and the weights, and that would yield a model that doesn't generalize. But there are definitely ways in which you can combat that. So, for example, you can search, you can optimize the architectural parameters on a held out data set, and then the weights on a training set, and so that would prevent you from overfitting. But just from our results, if we just look at it in absolute terms, and you compare to existing works, some of which start with a predefined model and they just quantize it or prune it, you see that our models generalize better to the test set. So I think that gives evidence that our approach does yield generalizable models. Let's see. Are there any techniques or better metrics that can handle these two problems? Yeah, I think, let's see. Yeah, I'm not sure how to answer that question because it's actually it's hard to say because every search algorithm can have this overfitting problem, and it really depends on what algorithm you use, and even like within a class of algorithms like Bayesian optimization, there are so many flavors, and they can have their own problems. I guess in general, the algorithms that do this kind of weight sharing mechanism that I'm describing can have this overfitting issue, but it's definitely solvable by just learning, for example, on a held out data set, the architectural parameters. Yeah. So yeah, I guess we can move to the next one.
Yeah. What do you imagine the Shannon limit to be here with respect to the compression results you cite? Is Vela close? How does one close that gap?
Well, okay, so I guess we could measure the limit, the compression limit, by doing like a calculation of the empirical entropy of the weights in the model, and then comparing that to Vela. I think from just intuitively, I think we're getting pretty close to the limit, because basically the decomposition that I showed here for the compressed model size, this is sort of like the optimal compressed model size, assuming that the mask and the quantized weights are independent of each other, and you can see that there's not much of a gap when you actually allow the compression algorithm to take advantage of compressing both the mask and the quantized weights. So I think we're quite close. How does one close that gap? I think we don't really have control over the performance of the compression algorithm because it's fixed, right? So the Vela compiler is given, and the hardware does the decompression, assuming a specific format of the compressed weights. So we don't have the power to change the compression algorithm. So we're sort of limited in the compression performance by whatever is inside Vela.
Cool. All right. I think that one more. Let's try to squeeze that in. We have a couple more minutes, so let's go ahead and take that one. For each of the UDC networks at different model sizes, do you need to perform a search for each of them from scratch, or can we extract different subnetworks from a one-shot trained SuperNet?
Yeah, we redo the search from scratch for each model, but there are ways to amortize that cost, not quite in the same way as something like the once for all, for example, approach where you train just a SuperNet alone with no constraints, and then you do like evolutionary search to extract subnetworks. We can do something similar, but not quite to that extent. But for all the results I presented, I did the search from scratch.
Okay. And then Nick's just jumped in just from that last question, and he's saying, to put a finer point on this, can you make Vela itself or the compiler in general parametric and learn this concurrently?
Okay, that would be quite intense. I guess like in theory you can, but I'm not sure how you would do that. I guess like practically it seems quite hard to me, because I guess you'd have to like describe what the compiler does somehow mathematically and in a parameterizable way. And I'm also not sure it's quite worth it, because you see already that Vela performs very well. Like we could maybe squeeze out another, I don't know, 5% or something in model size, and I'm just not sure that it's quite worth it.
Worth the effort. Yeah. So just lastly, then, if people who attended this, if they want to get their hands on this, is going to our ML eval kit for U55 the best way to get started?
So I think the two resources that are important for this would be like the paper, the unarchive that I think you posted.
Yeah, I posted. Yes. Yeah, I posted that link.
And then the ARM ethos compiler, Vela compiler. Yeah. So I'm not exactly sure. Yeah, I know there's like you can install it. It's open source. You can install it with pip. And I'm not sure exactly where like the reading materials are.
Okay, I'm going to put a link to the eval kit if anybody is interested in checking it out to try this. There is documentation there, and so if you just want to get your hands on it and try this Vela compiler out, this is where you can go and do that. So just between that and the archive paper, it should get you started with this if you're interested in trying this out. And then lastly, one last question that has come in: is Vela similar to what TensorRT does?
Okay, I'm not familiar with what TensorRT is. Could you? Okay. I don't know if you know.
Yeah. Srihari, do you have any? Can you clarify a little bit? Around TensorRT, like specifically, we'll give you about just a little bit to clarify, but.
I guess you also, in terms of information, you can also reach out to me. I'm happy to interact, like answer questions offline as well.
I will put your email in here. What's that? YegorFedorov@arm.com.
Oh yeah, but it's spelled. I'll put it. I think.
Oh, did I do it wrong?
Slightly misspelled. Yeah, it's okay.
Isn't it great when people misspell your name? Live.
I have a hard last name.
Oh, it's not that hard. It's a difference of a vowel. Okay, so thanks, Nick. TensorRT is NVIDIA's deep learning compiler framework. So yeah, if you haven't spent any time with it, I'm not sure how you would answer that question, but
I guess they probably do similar things like layer fusion, like fusing, let's say doing maybe like scheduling operators. I imagine they do something similar, but I know the one unique thing about Vela is that it does this, is that compresses models in its very specific way that can then be decompressed during inference by the hardware. So that might be one difference.
Cool. All right, well, with that, I think we're just about out of time. I really appreciate everybody showing up and hanging out with us for this past hour. I hope you learned something. I know I did, I always do. And thanks, Igor, for coming and talking about all the research and the work you've done in this space. So please check out the links. And again, if you have any more specific questions, please feel free to email Igor directly. He'd be happy to talk to you about this. Join us at our next Tech Talk. Go sign up and register. And with that, I will let you all go and have your day or your evening respectively. And we'll see you next time. Thank you so much. Thanks, Igor.
Thank you for having me.
Bye, everybody.